All right, well, good morning and welcome to week 2 already of Math 106. So today's plan, after we go over homework questions, is to continue where we left off, keep talking about the idea of these definite integrals and what they do, but we'll specifically address what happens when we have negatives, when our functions aren't positive, because right now you may remember, if you don't remember, but we kind of restricted ourselves to just positive ones. And then we'll get to the fundamental theorem of calculus, the fast way of doing these integrals. And we'll see why we talk about integration in the same class that we talk about differentiation. So that's our plan. I see that there are a couple of questions that people are asking about for the homework in the chat. I'm already seeing 4, 8, 14, and 18 from 1.2. I don't know if we're going to do all of those, but we'll definitely take a look at a few, some representative questions so that we can kind of get some things answered. Are there any others that people would like to look at? More than happy to add to the list. Okay, and then 1.1, number 13, part A from Alexi, 4 and 18, already on the list, Vanessa, but thank you. All right, so it looks like we have all kinds of good ones to go look at. So let me go ahead and share my screen. We'll go see if we can knock some of those out. All right, Fenway got that. All right, so 1.1, let's start here and let's look at number 13. All right, so when estimating distances from a table of velocity data, it's not necessary that the time intervals are equally spaced. After a spaceship is launched, the following velocity data is obtained. Use these, I should say, datum, to estimate the height above the Earth's surface at 119 seconds. All right, so we're making a guess. Right, we're making a guess at how high up we are. And all we're given are some velocities and some times. All right, so how are we going to answer this? How are we going to actually get distance from time and velocity? Like, don't even think calculus. Just go back to pre-calc days. If I gave you time and speed, how do you figure out distance? All right, thanks for throwing that in there. Alexi just put it in the chat box. D equals RT. I call that the DIRT formula, right? Because it spells dirt. Distance equals rate times time. So if we wanted to figure out the distance traveled, what we can do is we can multiply rate times time. All right, so rate is our speed or velocity. All right, so let's just take a look at what this is saying. It says it wants us to give a lower estimate of distance traveled and an upper estimate of distance traveled. All right, let's start with upper estimate because that's probably easiest. Like, what do you know for sure is a maximum distance that we might have traveled? From these numbers, what would you do to get a maximum number? Any thoughts? how about this? We know how long the spaceship's been going, right? It's been going for 119 seconds. So we have a time. Do we know how fast it was going?
4,093.
Okay, so we know its greatest velocity is the 4,093 feet per second. So at best, if we were going 4,093 feet per second for the entire 119 seconds, so I'll just write it in, we'll actually put in a number because it won't want it like that, right? But what I'm going to do is I'm going to take 119 and I'm going to multiply it by 4,093. Okay, so this is at best, as far as I can tell, since this is the greatest velocity that we're given, that this is by far the upper estimate of the distance that we could travel. Now, I know for sure we didn't go this far. Why do I know that this rocket hasn't gone this far? Let me grab my calculator while I ask that question.
All the other velocities measured are less than that.
Yeah, thanks, Reedy. So exactly, those velocities are lower. And so I know I'm not actually traveling 4,093 feet per second the entire time, right? So I know that this is going to be a maximum. So let me just go ahead and multiply these together real quick. So I get 487,067 feet. Now I do want to warn you, let me get rid of that again. This is asking us to give it in miles. And this might be one of the reasons why people had some trouble with this one, excuse me, is that this number, the 487,067 feet, is not miles. So we have to convert that to miles. And so I'm just going to put it in the chat box just here so we've got this written. There are 5,280 feet per mile. So we're going to have to end up dividing our number by 5,280 to get our number of miles. Okay, so that's going to be our upper estimate. So we'll take that number and divide it by 5,280. I don't know what that is, but 92.24753, blah, blah, blah. So since it says round it to one decimal place, we'll put it in as 92.2 miles. Okay, so that's like way upper limit, right? We're going to be something under that. But now what about the other one, the lower estimate? How can we get a lower estimate for this? All right, so Fenray just gave me 0. That's definitely going to be a lower estimate. How did you get that? Why 0, Fenray? Okay, so the 0 times 0. So doing the same kind of thing, but using the first row, saying that we're going, again, take time times velocity. All right, I definitely like your thought process. I don't like the 0 times 0. I don't like 0 times 0. But I think you could make a case for 119 times 0 because you're doing the same thing. You're saying, hey, let's just take our velocity, our lowest velocity, and multiply it by the amount of time we've been going. So you could do 0 times 119, which would give you 0. So that's definitely going to be a lower estimate. I would probably not multiply by 0. I'd probably multiply by 176. Just because the 0, while it is a lower estimate, is kind of a silly lower estimate. I know it's traveled more than 0 miles, right? I mean, that's kind of a duh. thing. So, but I would probably use the same kind of argument and go, well, the lowest non-zero velocity I've got is 176. What if I was going 176 feet per second for the entire 119 seconds? Clearly I'm not, right? Clearly I'm speeding up, which means the distance I'm traveling is going to be greater. So I would actually, in this box, do the 119. Again, that same amount of time, but now I would multiply that by my 176. So that gives me 20,944 feet, which again, I want to make sure I divide by 5,280 because I need to convert this to miles. And so that gives me 3.966666. So I would go ahead and round that to the nearest one decimal spot and make that 4.0. Because the 0 as a minimum distance is what we say in the math world trivial. That's a trivial answer. That's a, yeah. Everybody would know that regardless of what kind of data we get. But if we want this data to mean anything, then I would go with that lower velocity, 176. But I also didn't program this, so I don't know what answer it's looking for.
I want to throw out like what I did to get the correct answer for this one.
Okay.
Cool. So pretty much I did like left point estimation and right point estimation. And then in order to get what the times, I just took each value and subtracted it from the previous one. And
okay.
That gave me the, at the end I divided by 5,280. So.
Okay, so let me just translate, make sure I'm understanding what you're saying. So like in that first set where we go from 0 to 8, and we go up to 0 to 176, you basically were looking at making rectangle areas, if we want to call it that, right? And so the width of your interval was 8, right, from 0 to 8. And then for the height, you said you used the left end point.
Yeah, for the lower estimate. So
it would be, you'd have 0 times 8 for the first one.
Yeah,
and then,
I mean, mine had different numbers, but I've got my notes here. And,
right, but for this set, then it would be,
but yeah, it would be 8, 0, and then what is that, 9, 176.
And then 2 times 374.
Yeah.
And so on and so forth. Okay, cool. So a couple of things have popped up in the chat box here. So Lexi just said, don't you have to multiply each of them to find the area under the curve? Just like how much each time changes and use that as X. Okay, so do you have to? I love those words. Do you have to? You don't have to, right? Like, and I'll be honest, this is one of the things that sometimes gets me about homework questions like this one, is it just says, give a lower estimate of distance traveled. It doesn't say, give a good lower estimate, right? So like, think about that answer when Fenroy said at the very beginning, how about 0? If this is me, like if I give this as an exam question and you were to answer a lower estimate for this is 0, I'm giving you full points. Totally giving you full points because that is a lower estimate. That is below the actual distance traveled. Same thing if you say upper estimate and you were to say, well, let's take, say, 119 and multiply it by 1,000,000. Okay, sure, that's an overestimate. Now, what you guys are getting at, and I actually like this, is you're thinking, how do I get a better estimate? How do I get a better lower estimate? How do I get a better upper estimate? And in essence, you're doing exactly what we did before when we set this up with actual functions. So let me actually share a whiteboard screen and let me show you what I mean or how we could visualize this the same kind of way. Give me 1 second here. I have to adjust my screen so I can still see the data and write on the whiteboard. Okay, So basically, here's what we got going on. Let's draw a graph. So this is our time, and this is our velocity. And we know that distance is equal to velocity times time. So on this graph, since it's velocity times time, this is area. So here's your first like real application that we've talked about, that we've actually talked about in class. First real application of this finding area thing. That's not just area, right? It's not like we're really finding the area under here. We're using it to find total distance traveled. But we've got some data points. So let me just mark those data points. So we had 0, 0. We had 8, 176. We had 9, 374, or sorry, 17, 374. We had 19, 418. We had 43, 946, 60, 1320. I should have been a little bit more careful with my scale. 66, 1602, and then we had way over here like 119, and well, I don't have enough space, so we'll just call it like this. But if you were just to connect those dots to make a guess at what this function looks like, right? We need to say that that's f of x, that's our velocity with time. It's probably not exactly right, but it's close. And so think about what we did before when we went and we found the area for an underestimate. We always wanted to be under this graph. So in this case, we'd want to use left endpoint since we're going up. So we could end up with a graph that looks kind of like that, right? And think about how we did that before. We took the widths times the height. We took f of x times delta x. And so the f of x those were the velocity values. And the delta x, and this is something that Era has mentioned in the chat, we just get different delta x's. Those are the widths of those intervals. So like when Rigney was explaining what he did with the multiplying the width, the difference in the times the velocity, that was exactly it. This was our 8, 0 to 8 times 0. And then we had 9 times 176. And then we had 2 times 374, and so on down the line. So the left endpoints give us underestimates. And if we wanted overestimates, we just would have used the right endpoints to create our rectangles. So there we'd be using our bigger values. So this is going to give us a better underestimate or overestimate. And yeah, this is probably actually what the computer's wanting you to give as a value. But think about what I was saying, like when we first started, and said, well, let's just take our biggest velocity. And this is our biggest velocity. If I multiply that by the width, I get this big area. I guess the biggest velocity would be up here, right? But I know for sure that's going to be an overestimate. So the 119 times 4093 is definitely going to be bigger than the actual area. But I'm also incorporating a lot of extra area. So I'm going to be way over with that guess. And the same thing if we multiply by one of the smaller velocities, we're going to get a tiny rectangle down here. So, you know, something like, say, this rectangle, which I'm confident is going to be an underestimate, but it's going to be a way underestimate. All right, so in essence, it's exactly what we were doing before. We're just not given the function but we're given the function values, and we're also given a partition, if we want to put it into the language that we were using before. All those different times, when they're giving us velocities at those different times, we're partitioning that interval from 0 to 119 in this case. And so with that partition, using these data points, we can get estimates. All right, so how we feel about that one? Better?
I did it the same way that he did it, like by multiplying each one. When you did the left, right, you start at the beginning and you go one less because you're on the left side, and the right, you sort of start at the second, like just how I look at it, and you go to the last one. But every time the lower estimate, I think something with that 0 was making the number weird. So every time the second part, B, would be right, like the overestimate, but the lower estimate would be wrong every time.
Okay. I'll tell you what, that was you, Alexi, right? Just want to make sure I caught.
Yeah.
Yeah. Okay. I'll tell you what, I'll go look at yours, and I'll see what you did, and see what they were looking for. And it could just be something as simple as like a rounding error. If everything looks good, I'll go ahead and give you the point. But let me look at yours specifically and see if something funky is going on, because that process should work.
Okay, thank you.
Okay, so it sounds like you were doing it correctly. So let me see if we can figure out what the issue was, but at least the process is right, which is a good thing. All right, so are we good with this? What was this, number 13, I guess, from 1.3 or 1.1? All right, well, let me go back then to the homework page, and we will pull up the next homework set. And just pardon me for this delay. I have all kinds of, like, I don't know if you've ever tried to run a Zoom meeting. I'm going to guess that most of you have not. But you get all kinds of windows. Like I have a window that's got your pictures. I've got a window that's got chat. I've got a window that's my share controls, and all this stuff is getting in my way of navigating the web page. So talk about first world problems, right? All right, so this is probably as good a time as any to introduce this to this class. So some of you already know this. When I'm stalling for time, like while I'm waiting for the computer to pull up homework and all that, I like to tell really bad jokes. And I don't mean bad like, you know, raunchy. I mean bad like groaners, like dad jokes. So I'm always in the market for more of them. And just so you guys know what kind of jokes I'm talking about, let me give you one of my favorite math jokes. I know a lot of you have probably heard this one, but it goes like this. What did 0 say to 8? Nice belt. Yeah, think about it. Nice belt. Right, get it? 0 puts a belt on, scrunches down, looks like an 8. Yeah. Okay, so that's the kind of joke I'm talking about. So in the future, just so you know, when we're stalling for time here, I'm either going to tell you a really bad joke, or I'm going to request bad jokes. So please have your bad jokes ready. All right. So here's question number 4. Now, question number 4, it definitely looks like I've already done it. I think I was just checking to make sure everything was working. So let me just show you that what you can do. Suppose you do one of these problems and you get your answer, but you want to try another one just for more practice. You can always come up here where it says get a similar question, and you can click on that, and it will give you another one just like the one you did before. All right, and so we can try this guy again, but let's look at this one and see if we can figure out the answer to this. It says we've got this sum. Oh my God, that looks ugly, right? We got 1 over n, sum from 1 to n of 3 plus I minus 1 times 1 minus n to the 4th cosine 3 plus I minus 1 over n. So then it says express the limit as n goes to infinity as a definite integral, and that is provide a and b and f of x for this expression. All right, so let's remember what we were doing last time with the functions. We saw that when we wanted to make it an infinite limit, we could instead do it as a definite integral. And let's just kind of remind ourselves what the process was. So we took the entire interval from A to B and we split it into pieces, right? We partitioned it. We were smart about it though. We made it so that it was a regular partition so that each of those delta x's had the same width. And then we multiplied that by the function, but the function being evaluated at points somewhere in there. And we can use right endpoints, we can use left endpoints, whatever, but that was kind of the idea. All right, so let's see if we can kind of deconstruct this from our sum, remembering that our sum is a function times a width, right? Because we're getting area. So the function gave us the height, and then the interval width gave us our width. All right, so let's look at this thing. So in the sum, we've got all this stuff in the bracket, and then there's a times 1 over n. Okay, so one of those is our function, and one of those is our width. So it should be pretty obvious which one's our width, which is our width of the intervals. Is it all the stuff in the brackets, or is it 1 over n? All right, so a couple of you throw it in the chat, 1 over n. Right, it's 1 over n. The width is always going to be some number divided by n, right? So that number, like in this case, the 1, that's actually the total length of our interval. So what I know, but just by looking at this, is that the total width of our interval is 1. So from A to B, it's just a step of 1. So if I can figure out where we start, all I got to do is add 1 and I'll know where we end. Had that been 3 over n, the interval would have been length 3. So wherever I start, I add 3 to where I end. If it had been 12 over n, all right, my interval length is 12. Wherever I start, plus 12 is where I end, and so on. So the width is usually pretty easy to spot. It's just going to be some number divided by n. All right, so we know that the interval width is 1. All right, that means that this bracket contains the function. Now, here's how you're going to want to decompose this and figure out what the function is. Notice that here we've got this 3 plus I minus 1 times 1 over n, all to the fourth, and then that same thing inside cosine. Well, that 3 plus I minus 1 times 1 over n is basically how we're choosing our point to plug in, right? Think about it, as I changes, like when I is 1, plug that in, we get 3. When I is 2, we get 3 plus 1 I over n. So we just took 3 and we added 1 over n. Then we're going to add another 1 over n, then another 1 over n, then another 1 over n. We're adding the interval width each time. So this is the stuff we're plugging in. All right, so here's how I know what the function is. The function is going to be x to the fourth times cosine of x. Because notice that I'm composing into something to the fourth times cosine of that something. So that's how I can read what function this is. So now let's think about A and B. Where do we start and where do we end? So let's go back to where we start. And again, plug in I equal 1. If I is equal to 1, what am I plugging in? What am I plugging into the cosine, for example? So if I is 1, 1 minus 1 is 0. 0 times 1 over n is 0. 0 plus 3 is 3. Right? So I just plugged in 3. So 3 is my starting value. So how far am I going to go? where do we end? All right, thanks, Alexi. That brings us to 4. And again, we knew that because our interval was with 1. So let's just see if we got that right. Submit our question. Huzzah! We got it right. All right, now I want to try something here. Can I explain again? Which part there is? The function part or, okay, A, all right. So what I did was I started with my sum at the very first term. So I plugged in I equal 1. And when you plug in I equal 1 here, you get 3 to the 4th times cosine of 3. So are you cool with that part? Not necessarily the 3. Okay, so I'm taking 3 to the 4th cosine of 3. Now remember what we're doing is we're plugging in points in our intervals, right? So in the very first interval, I'm plugging in 3. Now, this one ends up being a left endpoint because of this I minus 1. Right? Think about when I plug in 1, this is saying take 3 and add no intervals to get the point that we're plugging in. No interval lengths. So that means that's my left endpoint. So since that's the left endpoint of the first interval, that makes A 3. That is the start of our interval. All right, cool. All right, any other questions on this one? All right, because here's what I want to do. I had somebody ask me a question and I don't know the answer to it. So we're going to test here. We're going to get a similar question. This time we're going to get it wrong, but we're going to see if we can actually get the correct answer. But then I'll change something here to make it wrong. So let's see if we can decompose this the same way. So we've got a new function, but we still have our width here is 1 over n. So here's our new function. So this new function to me looks like 6x squared, 6 times all this crap squared, minus 7x to the 4th. So I'm just using the structure and I'm thinking about all of this stuff. I'm just replacing it with an x in my mind. Then if I do that there, I do this here, I get 6x squared minus 7x to the 4th. All right, so can anybody tell me the starting point? Where does this start?
At 4.
All right, awesome. Yeah, thank you, Diego, Fenrui, and I think that was Susanna I just heard. But yep, it's definitely 4. If you plug in I equal 1, this goes to 0, and we're left with 4. We're plugging in 4. So we're starting at 4. And where are we ending? Good, Aries. We're ending at 5 because it's 1 over n. Okay, so this is actually the correct answer, but I'm going to tank it. So I'm going to make it 5.1 because I just want to see if my score goes down. So I've got 10 points right now. I want to see if I lose some points on this. Okay, so clearly I got that one wrong. I got my 2/3 out of it. All right, so I'm going to check my score later, and this way I can get back to whoever it was that sent me that message, and I apologize for not remembering who that is if you're in here. But I don't believe that it actually, oh, that was you, Juan Carlos. Okay. I don't believe that it actually does cause your score to go down, but I don't know for sure. So I'll find out in a minute. I think it keeps your highest score. Once I figure out the answer to that, I'll reply to your email. All right. Anyway, so there's number 4. Hopefully we're feeling a little bit better about how that works and how you can picture what that function is. You can just imagine how horrible it would be to try to do this sum. We haven't even talked about what happens when you take an I to the 4th and get its sum. Think about the other one that had like a cosine. Oh, good Lord, these are horrible. That's why it's going to be really nice that we create a faster way. All right, so let's go take a look at number 8 here. Okay, we're not going to do number 8 just yet because we need to talk about that. That's one thing I haven't hit yet in class, so we'll get to that in a second. Let's see what number 14 looks like. Oh, okay, let's look at number 14. This one looks brutal, huh? So we're integrating, we're doing a definite integral, so we're doing that whole find the area under the curve, whatever. And this is our function. Cosine of natural log, or cosine times natural log of 1 plus x squared plus x to the 4.8 divided by 1 plus e to the 1.86 x minus 70.6. And some of you probably looked at that and cried a little bit. Maybe the flame of math excitement got extinguished inside your heart. And you just went, yeah, oh, good Lord, I don't want to even try to do this as a sum formula. Well, don't let that cause you too much trouble. Yeah, come back here and look at your bounds. This is saying we're going from 2 to 2. So what do we know is the case with every integral if we go from the same point to the same point? Yeah, it's just 0. This is like the easiest question in the world if we recognize those bounds. So pay attention to the bounds. They can definitely save you some time if you recognize that, like in this case, they're the same. So I'm going to take my points because I want my points. Look at that, 10 out of 10. That was the easiest 10 points in the history of points. But again, only because we recognized those things are the same. Oh, and please take when I say it was easy, take that with a grain of salt, because I know that whoever asked for this, and I think there were multiple people, you might go, oh, it's not that easy. You know the definition of easy, right? Something's easy if you know the answer, if you know what to do, right? Like trivia. If there's a trivia question, you go, oh, that's easy. Yeah, it's easy because you know it. If you don't know it, it's hard. And I'll probably say some things are easy that aren't really easy just because I know calculus. But I would say that one, if you recognize that those bounds are the same, then we end up getting 0. Okay, 18, this is another one I want to hold off on because we haven't talked about it yet, but we will as soon as we're done here. So I'll come back to 18 and 14, or sorry, 18 and 8 in just a little bit, or potentially I might leave it to you guys once we talk about what those things mean. All right, so speaking of those new things, I think we should probably go ahead and march in there. So there are just a couple of things from 1.2 that I have to finish out with you guys. I want to talk about what happens when we have negatives, and that's what happened with number 8, that homework that I skipped over, is that function goes negative, and we need to talk about what that means. I do want to talk about average value of a function. It's actually really easy to do, but we need to know average value before we move on. And then after I knock out those are the last remaining things from 1.2, we'll get into the fundamental theorem of calculus. We'll get into this biggie that actually makes it so that we can do the stuff in a much faster way. We don't have to do the sum formulas anymore because we're going to be smart. We're going to think about it like mathematicians, and we're going to generalize, and we're going to go, okay, I don't care what my function is. How can I work this so that I don't actually have to do sums anymore? Okay, so give me 1 second. I'm going to hop up to the whiteboard and we will move along. All right, so let's just kind of remember what was going on with the integrals. When we were integrating, say from a to b, f of x dx, remember what we were thinking about here is that this was a sum. This was a limit as n goes to infinity of the sum from 1 to n of f of xi times delta xi. Right, that's where this came from. And in the context of what we were doing, this found the area, right? This was the area under the curve. Because we were answering the area question, right? And that led to the creation of this integral. Now, when we were doing this and we were finding areas, we were specifically told that our functions had to be positive. Let's look at what happens if our function's negative, and we'll use this as just a practice for finding the sums. But here's what we're going to do. Let's find the integral from 0 to 1 of x minus 1 dx. So this will be our warm up with the sum formula stuff, because we haven't actually run through one of those in a bit. So let's see if we can find this integral. So we're not going to draw the graph. We're not going to do anything. We're just going to dive right into the sum formula. Okay, so let's think about what our process was, what we had to do. First, we had to get our interval width. All right, so Susanna, you're already saying that this is 0. That's bold, be throwing out an answer this quickly. We'll see. We'll find out if that's actually correct or not. But what we have to do is we have to take our interval and we have to split it. We have to partition it. So remember how we find the width of the intervals, right? The delta x, that's going to be b minus a over n. Always b minus a over n. Always, always, always. So in this case, that's going to be 1 minus 0 over n, or 1 over n. So the widths of our intervals here are 1 over n. Okay, so then we have to choose left endpoints, right endpoints, whichever one we want to plug in. I suggest we use right endpoints. It's a little bit easier in the formula. If we use right endpoints, that means that our x of I is going to be 0 plus I times 1 over n. Hold on here. Let me do it generically again. It's a plus I times delta x. Okay, so if you use the right points, we're always plugging in a plus I times delta x. If you use left endpoints, it's a plus I minus 1 times delta x, kind of like we saw in those homework problems. But if I'm going to actually evaluate this limit, I want to make it easy on myself, which is why I just do I times delta x instead of I minus 1 times delta x. All right, so in this specific example then, this is going to be 0 plus I times 1 over n, or I over n. All right, so we've got our widths. We've got what we're plugging in. So now let's create our limit. So this is going to equal the limit as n goes to infinity of the sum from 1 to n. We're going to plug in I over n. So we're going to get I over n minus 1 times delta x, which is 1 over n. So the I over n minus 1 That's coming from my function. Remember, my function was just x minus 1. So I'm going to take my x, I over n, and subtract 1. All right, well, let's do this limit. So we got to start with the sum. I'm going to pull the 1 over n out front because it has nothing to do with the I, so it'll make things a little bit easier for us. All right, so here we go. I need to do 1 over n times the sum of the i's. And the formula for sum of i's is n times n plus 1 over 2. And then I'm going to subtract the sum of 1. Well, 1's a constant. And what we saw is we take that constant times n. This is just going to be minus n. So those two came from the sum formulas. The n times n plus 1 over 2. That was from the sum of I. And then the n over here, this was the sum of the 1's. Okay, so that's where those came from. All right, so now let's evaluate this limit. I'll run it over here. So let's simplify a little bit first. Let's distribute that 1 over n through. So we're going to get the limit as n goes to infinity of n plus 1 over 2n minus 1. So the 1 over n canceled with the n on top as I distributed through, and then reduced with the n on the very end to give me this. So now when I evaluate my limit, I use the, since I've got a fraction, I can look at the degrees. They're both degree 1. Take the coefficients, I get 1/2. I subtract 1, and we get negative 1/2. So all of that work was just using the definition, and we ended up with negative 1/2. And it's probably at about this point that you start going, what? I thought we were finding area here. And getting a negative number is nonsense for area, right? That doesn't make sense. We shouldn't get a negative number. But here's the deal. This function is not positive here. Let's draw a graph. Let's actually draw a graph of this function and see what it looks like. So you can see what's going on here. So here are axes. We've got y equals x minus 1. That's a line. It's got a slope of 1. It's got a y-intercept of negative 1. So it looks something like this. We are between 0 and 1. And so notice that in this interval, we're actually below the x-axis. Okay, so we got a negative 1/2, but if I were to ask you, what is the area between this graph and the x-axis? Like if I were to ask you what this area is, could you answer that? Hopefully the answer to the question is yes, I can answer that. Because that's just a triangle. What's its area? All right, so the area is 1/2. It's good old 1/2 base times height. Thanks for that, Juan Carlos. So it's 1/2 base times height. This is height of 1, a base of 1. 1 times 1 is 1 times a half is a half. So this area actually is 1/2. So notice that the number we got, while not the area, is definitely related to the area. And what we ended up getting, this is just the negative area. So this is what's going to happen if our function's actually negative. We don't change the definition of the derivative. We still do the same thing. We still do a limit, an infinite limit of that sum, right? So it's an infinite sum, same structure, sum of f of x times delta x. It just ended up giving us a negative number. It gave us the negative of the area. So what I like to say, and what you'll see, I think this is actually a math term. I don't think this is just a Bruceism. But I like to say that integrals, they don't actually give us area. They give us signed area. And when I say signed, S-I-G-N, signed, that just means it's positive if f of x is greater than 0. And you get negative area if your function is negative. So in a situation where you actually are below the x-axis, it's giving you the negative area. All right, so technically, if you want to calculate the area between a function and the x-axis, so even if we're like going to go down here and we actually want the positive, the way you would get positive is by doing an absolute value, right? So technically, for any function, here's how we would do this. So for any function, the area between f of x and the x-axis it's the integral of the absolute value of f of x. So when we were doing this before and we said our function was positive, we didn't have to worry about absolute values. But if we allow our function to go negative, we have to realize that all the stuff down below is actually going to give us a negative number. All right, so this is technically what's going on if we want to find area. We've got to be really careful. If our function is positive, no big deal, we just integrate. If our function is negative, or negative at any point, we have to keep that in mind. Because anytime we dip below the x-axis, we're actually basically we're taking value away from our integral. Where if we're trying to answer an area question, that's a problem. All right, so if our graph dips below the x-axis, we actually get negative of the area. So I want to go ahead and share my screen, and we're going to go back to that homework question, the first one that I skipped over, and see if we can answer it now. I think that was question number 4. No, question number 8. There we go. All right, so let's look at this one. And this function definitely sometimes is positive, sometimes is negative, right? And we want to find the total integral. All right, so they told us some areas here. They say the areas of the labeled region. So A1 is 5, A2 is 4, A3 is 1, and A4 is 1. All right, so let's just talk about some different integral values for this guy. Specifically, this one's saying, let's look 5 to 10. So from 5 to 10, that's just looking from 5 out to 10. So that's only A3 and A4. Now A3, they tell us is 1. So that's going to give us a positive 1 when we integrate. A4, we're told that that area is also 1, but when we integrate, that's going to give us -1. All right, so if we put that all together, what we're going to get for this v, for this value, is going to be a +1 -1. So this one's going to give us 0. So let's get some points there. Look at that, 10 out of 10. So that one gives us 0. All right, so I don't know if you guys can see on the whiteboard, but let's do the same problem, but let's look at an integral, say 0 to 10. So we're going to do the same one, but let's do 0 to 10. What value are we going to get if we integrate the whole way from 0 to 10?
Would it be 1?
All right, it absolutely would be 1. Because now, again, think about those yellow goldish ones. Those are going to be positive. So A1 and A3, that's 5 plus 1 is 6. So we've got +6. The blue ones are going to be negative. Well, that's 4 and 1 is 5. So we have +6 minus 5. And so that integral would equal 1. All right, how about the integral from 3 to 7? So let's do the same function here, but let's just go from 3 to 7.
-3.
All right, good, Susanna. And error is -3. It's exactly right. It's going to be -3 because A2 gives us -4. A3 gives us +1. Therefore, our total is -3. All right, so hopefully that makes a little bit more sense. But you can see that it's actually a pretty easy thing. Just we have to recognize that if we're below the x-axis, we get a negative. All right, so this actually brings me to another point that I think is really, really important. We teach you about integrals using the area idea because that's how it came about, right? Historically, that was the question that was trying to be answered. And it's also really easy to see geometrically. But here's what I want you to really get from this is that integrals don't even give area necessarily, right? I mean, we've already seen that getting a -1/2 doesn't even make sense. And saying that it's signed area. Here's really what integrals do. Okay, this is really important. And I'm going to drill this into you pretty much every day when we talk about integrals, just because I want you to know this. What integrals really do. Integrals add stuff up. That's really what we're doing when we're integrating, is we're adding stuff. I mean, think about it. It was a limit of a sum. So a sum, that's adding a bunch of stuff up. And then the limit makes it so that we're adding an infinite number of them. Okay, it just turns out that in the example we were looking at, we were adding up areas, right? We were adding up areas of rectangles. But what you're going to see from here on out when you do integration is that you use integration anytime you want to add a bunch of stuff. And it doesn't have to be areas. It can be lengths. If I want to add a bunch of lengths, I can use integrals. If I want to add a bunch of forces, I'm going to use an integral. If I'm going to add a bunch of insert your favorite quantity here, that's where we're going to use integrals. So integrals are used all kinds of places, well beyond just finding areas. It's just areas are a real easy one for us to start with. But I don't want you to get trapped into thinking that integrals are always area, because they certainly are not. They're used for so many more things. So just realize anytime we want to add stuff up, we're going to go to an integral. All right, so now we know what happens when we have negatives. It's really the same idea. we're just getting negative area if we're looking at the graph like that. Or if we were talking about, say, like velocities, remember that first question that we did on the homework that had a bunch of velocities and times? If we had negative velocities, meaning going downward, okay, do the same thing. We can use those velocities times time, get a distance, and we want a negative distance. We drop down, or whatever it happens to be. All right, so cleared up the, what do we do with negative? Now, the other remaining thing from 1.2 that I want to talk about real quick, and this will help us answer that other homework question, is average values. Average values of functions. So if I give you a bunch of numbers, how do you find the average? What do you do to calculate the average of a bunch of numbers?
Add them and divide by the number of numbers.
Okay, so you add them all up, and then you divide by how many there are. Okay, so if we're going to do an average of a function, average value of a function, it's going to be the same thing. We want to add up all the function values and then divide by how many there are. That's just what it means to do average. It's actually what we call an arithmetic mean, but it's all good, right? So we're just going to find the average. So think about what we're going to do. We're going to add up a bunch of function values. Okay, so what do we use to add lots of stuff up? These integrals. Okay, so here's what we're going to do if we want to find the average value of a function. Now, first of all, we have to know where we're looking to calculate an average value. Because if I just said, hey, what's the average value of, f of x equals x squared? You might go, well, from where to where? Because if I go from -1 to 3, I'm going to get something different than if I go from 0 to 2, different than -100 to 100, right? Like, I mean, it matters, right? So what we're going to say, we're going to look at the average value of function. So let's say we've got f of x on an interval a to b. All right, well then this is how we define the average value. So I'm going to write this as f avg sub avg, so f average. So we have to add up all the function values. So we're going to add up from a to b f of x dx. All right, we're going to add them all up, and then we have to divide by how many we have. Well, the number that we have is the length of the interval. So thinking about this and looking at this structure, this is exactly how we find average, right? This is add them up, and then we divide by how many? Right, when I ask how we find an average, that's what Susanna said before. That's exactly what we're doing here. So you'll often see this instead as written as 1 over b minus a times the integral. I think that's what you'll see in your book, but you can go ahead and box this, because this is how you can find the average value of a function. So basically you just integrate it, and once you've got that integral, you divide by the width. So think about that one that we just did, the one that gave us a -1/2. All right, so that one was integral from 0 to 1 of x minus 1. So its average value would be 1/2 divided by the length of the interval, which was 1. So its average value is -1/2. So it's actually really easy to do. You just got to divide by the length of the interval. So let me share my screen again, and we'll go look at the other homework question that we skipped over. And I forget the number. Was that number 18 or 14? Anyone remember? Must be 18, because 14 we've got points on. Okay, so for this one, it says find the average value of f of x equals x to the 7th between -1 and 1. And then find a number where f of c equals that average. So it's saying not just find the average, but then find out where our function actually equals that average. All right, well, let me show you how we're going to set this up. We're still not going to answer it just yet, but I want to at least show you how we're going to set it up. All right, so we are finding the average value of f of x equals x to the 7th. And we're on -1 to 1. So let's set it up. The average value is going to be 1 over 1 minus -1. That's 1 over b minus a times the integral from -1 to 1 of x to the 7th dx. All right, so this is going to be 1/2 times the integral from -1 to 1 of x to the 7th dx. All right, so we need to calculate this integral, and we can go to the we can go ahead and do the sum formula if we want, but I don't want to, because we're going to have an x to the 7th and I to the 7th, and I don't know about you, but I don't know the form or the sum formula for I to the 7th. So instead, we're going to be a little bit tricky, sneaky. Let's draw a picture of it. Let's look at x to the 7th. All right, so x to the 7th looks something like this. So there's our graph of x to the 7th. Make this a little bit darker. All right, and we're going from -1 to 1. All right, so remember what the integral does. When it's positive, function positive, it gives us the area. And when it's negative, it actually gives us the negative area. So that bit in purple is going to be negative, and the bit in the teal is going to be positive. All right, so what do you think? What's the answer to this going to be? Yeah, thanks, Mariola. She just threw in the chat box 0. All right, it turns out that this integral from -1 to 1 of x to the 7th dx is equal to 0. You guys good with that? I mean, we might want to be careful, because just because it looks like it, be very careful, especially with my drawing. It looks like. Might look like those cancel out, but we need to make sure. But this is definitely true. This is going to equal 0. The positive part is going to be the same as the negative part. So this ends up then being 1/2 times 0, which is 0. So it turns out the average value of this function is 0. All right, well, Mariola, how did you know it was 0? Or did it just look like it and that's why you said it?
Because it looks like they cancel each other out, like at the example, the homework example, and also it's a function they have to be equal, right?
Okay, so it's because this is a special kind of function. You remember what we call these kind that have this kind of symmetry? And this I'm opening up to everybody, not just Mariola. There you go. Thanks, Harris. It's an odd function. Odd functions have the symmetry where it's that rotational symmetry about the origin. And so here is a fact for you. All right, you can put this in a box because it's definitely 100% all the time, and we can use, and we'll use it a lot. If f of x is odd, so insert your favorite odd function, then the integral from minus a to positive a of f of x equals 0. So if those bounds are opposites of each other, you're going to get 0. And that's just making use of the symmetry. So when we've got an odd function, like in this case, x to the 7th, seeing that those bounds are opposites is actually huge. Because then we can go, cool, this integral is 0. The positive and the negative cancel each other out. All right, so the whole even odd thing, you may have wondered back in the day why we care about even functions and odd functions. And probably the argument before was, well, just to make the graph easy, you can draw it fast, just use symmetry, blah, blah, blah. There are lots of places where even and odd are really useful, and integration is one of them, right? Because if it's odd, we can do this. What if it's even? So let's do another one here where we say f of x is even. What happens now if we integrate from minus a to a? Think about what an even function looks like. Even function has symmetry. It has reflective symmetry over y equal x. So here's an example of an even function. Right, it's got mirror images here. And now we're going to integrate from minus a to plus a. What do you notice about this one? Well, they don't cancel each other out now, right? Like these are both going to be positive. They're both going to give us positive numbers. But if you look at the bit on the right versus the bit on the left, they're exactly the same, right? So I like how Eric just put times 2 with a question mark. Oh, that's absolutely what we're going to get. We're going to get double the integral from 0 to a of f of x dx. The integral from 0 to a is just this piece that's on the right. But if I double that, I get the total. Now, this one's not quite as nice, right? Because we're still going to have to calculate this integral. But I want you to think about actually doing the integrals. It's going to be a lot easier if our endpoint is 0. Because think about what we were plugging in. We were plugging in a plus b minus a over n times I. It's a lot easier if we do 0 plus something, right? 0 plus something, no, that 0 just goes away. So it definitely makes the calculation easier if our bound is 0. So when we've got an even function, we can definitely make use of that. I don't know, weird little places where all this stuff comes in. But this also illustrates why everything we told you in pre-calc, literally everything we told you in pre-calc is going to be used somewhere. So you can go back and look at your notes from that year of pre-calc, and yeah, everything in there we're going to use somewhere. in calculus. Here's where even and odd is definitely useful. All right. So maybe we need to figure out the faster way of doing this, because doing a sum formula is going to be a bear, right? And think about that example that we just looked at from the homework with the x to the 7th. What if the bounds hadn't been minus a to a, right? I mean, we got lucky there. It was minus 1 to 1, so we could just jump straight here and write that the area was 0, or the integral was 0. But what if it had been minus 1 to 2? Then we would have been SOL, right? It wouldn't have been beneficial. So we need a way of doing it in a way that's faster. And that's where the fundamental theorem of calculus is going to come in. So let me just jump straight to it. Now, the fundamental theorem of calculus actually has two parts to it. And I'm going to show you, I think just one part with our remaining time today. Yeah, I'm definitely just going to show you one part. So we'll look at the second part on Wednesday. And I'm going to show them to you in a different order than the book shows them. It doesn't matter. I mean, they're both fine. Either way is fine. But I'm going to actually show it to you in the other order, because I want to show you the one that will answer the question we're doing right now. What is the faster way of doing these integrals? All right, so here's what the first part says. We'll call this guy part 1. What it says is that if you integrate from a to b, f of x dx, you actually get big F of b minus big F of a, where big F of x is an antiderivative of little f of x. So hopefully you remember antiderivatives, which is differentiation going backwards. That's why we use the capital. The capital is generally, capital letters generally used for antiderivative. All right, so here's the first part of the fundamental theorem of calculus. It just says that if you want to integrate, what you can do is just find the antiderivative, or find an antiderivative, doesn't matter which one, and evaluate that antiderivative at the endpoints, and then subtract. So before I prove it, because I will prove it, but before we prove it, let's just use it a couple of times. Let's see how fast this is and how much better it is than doing that area stuff. So we're actually going to tackle some that we've already done. So let's start with the very first question that where we attack this area idea. We are looking between 0 and 4 of x squared dx. Oh, actually, that's not true. Was it x cubed? No, it was x squared. I think this was right. 0 to 4 x squared. Regardless, let's see if we can do this. So before we did the sum formula, we took 0 to 4, split it into pieces so the widths were each 4 over n. Then we plugged in endpoints, so we plugged in 4 over n times I into this, and we distributed blah, 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 right? Okay, let me show you how fast this can be using the fundamental theorem. So what we need is an antiderivative of x squared. All right, so do you guys remember how to do an antiderivative of a power? Anyone remember the power rule for that?
Would it just be 2x because the exponent moves to the front and then it lowers by 1?
Okay, so that's if we differentiate, but we want to go backwards. So what you just gave me, Susanna, is the power rule for differentiation. But for anti-differentiation, so Bruna just put in the chat box 1/3 times x cubed. And that is absolutely correct. So we've got big F of x is equal to 1/3 x cubed. Instead of bringing the exponent out front as a multiple and subtracting, we add 1 to the exponent and divide. So we're just doing the same thing backwards. So we get 1/3 x cubed. And then I saw somebody, I think that was Rigney, put in on the chat box plus c. Good job remembering that. We can add any kind of constant we want and still have an antiderivative. Okay. So the group of all antiderivatives here is 1/3 x cubed plus c. Now, if you come back and you look at what I wrote here, f of x just needs to be an antiderivative. It can be any antiderivative we want. So because it can be anything I want, I'm going to pick c equals 0. And I'm going to recommend that you do that every time. If you don't want to, that's fine. Add on your favorite number. Make it 1/3 x cubed plus 5. 1/3 x cubed minus 48. It absolutely doesn't matter because it will end up canceling itself out. All right, so here's what we need to do then. We need to evaluate this at the endpoints. So we need to do f of 0, and we need to do f of 4. So if I put in 0, I get 0. If I put in 4, I get 64/3. So that means that this integral from 0 to 4 of x squared dx is going to equal 64/3 minus 0, or 64/3. And if you go back and you look at your notes, you'll see that when we did the whole limit definition thing, we ended up getting 64/3. Way faster. Oh my God, way faster doing this than the whole limit definition thing. All right, so here's that one. The integral of x squared. Let's look at the one that we just did today, the one that led to the -1/2. That one was the integral of x minus 1 from 0 to 1. All right, so let's get an antiderivative. So x, what's its antiderivative?
X squared.
All right, x squared, almost. There's another little bit to it. All right, good. Thanks, Stephanie. We have to divide by 2. So we add 1 to the exponent, but then also divide by that value. So you were really close, Mariola, but it's going to be x squared over 2. How about the -1? What's its antiderivative?
X, negative x.
Good. So we have minus x, and then we're not going to bother plugging anything on there. So this is our big F of x. Now, what I want to show you is the shorthand that we use to show that this is the antiderivative, and we still have to plug in the points. What we're going to do, we're going to put this so that we've got a parenthesis on the left and a bracket on the right. Sometimes you'll just see a vertical line. I like to use a bracket. And we're going to put our endpoints still up there. Now, this is, again, not a Bruceism. This isn't just that I do this. Like, this is very common to see. But basically what you do is you put your antiderivative in here and then you still have your bounds. So now we know we need to plug in those bounds. Right? We need to do f of b minus f of a. So we'll plug in 1. We get 1/2 minus 1. And then we have to subtract what we get when we plug in 0. So f of b minus f of a, which is negative 1/2 minus 0, or negative 1/2. And again, fast, easy, and we're done. Okay, so this is how the fundamental theorem of calculus works. It is the fast way of getting our answers. All right, but we got to prove it. We got to prove it. Can't just take it on faith. Plus, this is like, I mean, it's called the fundamental theorem. We should know where it comes from and how it works. All right, so let me real quickly, before we call it a day, give you the proof of this. So you can see where it comes from. Okay, so let's go back to the mean value theorem. Remember the mean value theorem? And it's okay if the answer is no. Do you remember the mean value theorem? How about we go, do you remember hearing that there was a mean value theorem? Okay, so hopefully at least the words mean something to you. It's not the guess and check one, but the mean value theorem. This was the one that said if you have a function and you were to look at the slope of the secant line, the slope of the line from the endpoints, we know that somewhere in that interval, it's a continuous function, somewhere in that interval, we have an instantaneous rate of change or a tangent line that has the same slope. So the mean value theorem just says that somewhere in your interval, there's a place where you have a tangent line slope that's the same as your secant line slope. Okay, that was the mean value theorem. So we're going to apply that to big F. So let's apply the mean value theorem to big F of x on the interval AB. So that tells me that there is some place C in AB where the derivative of big F is equal to big F of B minus big F of A divided by B minus A. So that right-hand side, that's just the slope. That's the slope of the secant line. And I know that this is how this is. Okay, so I know that this is true over the entire interval. And if I was on any interval, if we did the same thing, so we'll just call this xi and xi plus 1. So those are just two x's somewhere. We know that there's going to be some place in there, I'll call it ci, where I get f of xi plus 1 minus big F of xi over xi plus 1 minus x of I. All right, so this is just super generic. Take any 2 points, call them xi plus 1. This is what it looks like. To help us out, because it's a little cumbersome, let's call this delta xi. And I'm going to rewrite this so that I've got f of xi plus 1 minus fx of I equals f prime of ci times delta xi. Just got rid of the fraction. Okay, so you're looking at that and you're probably going, okay, whatever. Right. Well, this is just what the mean value theorem says for this function. All right, now let's kind of bring it back to what we were trying to do. We're trying to find an integral from a to b, right, of this f of x. So here's what I'm going to do. Let's take that a to b and let's partition it. So we're going to cut it up into a bunch of pieces. And what I'm going to do is I'm going to add a bunch of those things and basically do your infinite limit idea. But let's just start with the sum. We're going to do the sum from 1 to n of f of xi times delta xi. Well, check this out. Look at that and compare it to this form right here. These are equivalent. I mean, yeah, I call that one big F prime, and this one is little f. But isn't that what big F prime is? The derivative of an antiderivative is the function itself. Okay, so I'm going to add a bunch of these things up. So what this sum is actually telling me to do is to take f of x2 minus f of x1. I'm going to add to that f of x3 minus f of x2. I'm going to add to that f of x4 minus f of x3, and so on and so forth. Right? I'm just adding up all these differences. And the very last one, there's going to be a f of xn minus f of x of n minus 1. So this is what we call a telescoping sum. Check this out. Lots of stuff cancels. I've got an f of x2 cancels with this minus f of x2. There's an f of x3 that cancels with a minus f of x3. The f of x4 is going to cancel with the next one, and the next one, and the next one, and all kinds of stuff is going to cancel. We'll cross that one off. We'll cross that one off. All right, so we're almost there. So check out what happens. We break this down into a bunch of pieces. We partition it. We take that limit as n goes to infinity. And what we're left with then is the integral of f of x dx from a to b, right? That's the sum. And look at what remains. There's a minus f of x sub 1. And if you remember what x sub 1 was, it was the left endpoint of the furthest left interval. And we're left with an f of x sub n, which was the right endpoint of the rightmost interval. Those are supposed to be capital F, sorry. And so what we're left with then is f of b minus f of a. This guy's f of b, that one's f of a. All right, so there you go. There's the proof of the fundamental theorem of calculus. It actually comes from the mean value theorem. So you may look back at last quarter and go, why the hell do we care about the mean value theorem? It seems stupid. We never used it. Yeah, you're right. Well, we kind of used it. But this is why we care about the mean value theorem, is because it gives us the fundamental theorem of calculus, which means we've got the fast way of doing integrals now. So if you go back and you look at all those homework problems that you guys have done in this last section at like 1.2, you could bang them all out in no time now, because we got the fast way. It's kind of like with derivatives. You may remember when you actually had to calculate the derivatives using the limit definition, it took a while. And then we learned the rules the fast way, and then we were done. We're kind of in that same place. But don't forget how integrals work, that we're adding up a bunch of stuff, because that's super important to remember what they do. But this is going to be our fast way of doing the calculation. All right, and I don't remember who this was, but someone last time, I think when I was doing this, said, oh, well, isn't there another way? Can you show us the faster way? And I said, hold off until the fundamental theorem. I think, was it you, Alexis? I want to say, but whoever that was, maybe this is what you were talking about. And we will definitely do more of this, because this is how we're going to always do it. We're going to find antiderivatives, and we're going to plug in endpoints. Oh, that was you, Alexi. Okay. But this is going to be the way that we do it, pretty much from here on out. But remember, this is only half of the fundamental theorem of calculus. I said there was a second part. There's a part 2. We'll look at that next time. Okay, so our goal next time is going to be to look at the second fundamental theorem of calculus, and then keep playing with these things. And so basically from here on out, it's going to be, let's develop rules to do the integration faster. Let's find ways of finding the antiderivative quickly. You already know how to do it for certain things, right? Like powers are easy, some trig forms are easy, right? You already know how to do it for a lot of things, but you're still really limited. Because like if I were to ask you, what's the antiderivative of natural log of x? You're all going to go, we've never seen anything whose derivative is natural log of x. So that's what we're going to be doing a lot this quarter, is developing techniques for finding those antiderivatives so we can use the fundamental theorem of calculus. All right, so I think we're going to go ahead and call it a day. Oh yeah, I'm a little bit over time, I apologize. So let me go ahead and stop our recording.